Okay, I think we can start. So I will start with a question. Maybe someone know how many public libraries are available in Java currently? Maybe someone know. We have already almost 14 million projects in the Maven repository alone. And this is as much as 36% of the population of Poland. So quite a lot, yes? And now we can ask how many of these projects introduce important changes for us during a year. Definitely less than 1%, yes? And next question will be, how often are fundamental changes introduced to the Java ecosystem? Very rarely. Most often as a part of new language version like Java 8 or Java 11. And as you may know, just 2 days ago, a new JDK version was released, JDK 19. And in my opinion, we have in Java 19 one of the most important features added to the Java language during last years. It is named virtual threads. And in my opinion, it can have a very big impact on the usefulness of the reactive programming, which is quite widely used today in Java. And because of that, and because of I am a big fan of reactive programming, I want to share my thoughts on this topic. My name is Łukasz, I'm a software developer, and today I'm going to answer the question, what is the future of reactive programming? But before we get to the point, I would like to make a short introduction for those of you who don't know what reactive programming really is and to solve what problems is most often used in Java. So until recently, most of IT systems around the world have been created based on a monolithic architecture. It is one in which all main components operate as a single process. And this is a very simple architecture, and it is sufficient for, small services. So if you have some small shop or any other small application, the monolithic architecture will be sufficient for you, yes? But nowadays, when new systems are becoming more and more complex, a monolithic architecture is often abandoned in favor of the microservices architecture, which allows us to avoid many common problems by dividing a system, especially a big one, into smaller parts. This solution has, of course, a lot of advantages, but also has several disadvantages, which should be considered when choosing it. Some of them can be easily eliminated by the appropriate design of the system. Others require the use of the appropriate technologies. One of the most important of the latter, which I want to focus on today, is the possible performance drop caused by the blocking communication between microservices. And the blocking communication is something really important for us today, so I would like to explain it quickly. I will try. Let's imagine that we have two HTTP services, Service A and Service B. Service A exposes a public API to the end user, and Service B exposes an internal API for the use by the Service A. When Service A processes a request, it has two parts, a part that requires an active attention and a part that does not. A part that requires an active attention is called CPU work, because it requires central processing unit to actively spend time thinking and computing result. The part that doesn't require an active attention is called I/O, which stands for input-output, because it involves waiting for something else to provide input or to send output. In our case, a thread which sends the request from the Service A to the Service B have to wait for the network operation to finish, so for the response from Service B. And it's a blocking communication, because the thread is idle waiting for its completion. When the thread is blocking, this thread is parked using the native unsafe park invocation and idle waiting for someone to unpark it. In our case, unpark will be called at the time of receiving response to the Service B. And let's imagine that we have to handle thousands of requests. So we have to create thousands of threads. And theoretically, it's not a problem, yes, because modern operating systems allows us to create many more threads than the number of central processing units that we have. But threads are expensive. Their biggest disadvantages are a long starting time, a size, and the cost of switching between them. A problem with a long starting time can be easily fixed by pooling the thread. So instead of creating a thread when we need it, we create a thread pool and reuse the already created threads. Yes, but the problems with a size and the cost of switching between them are hard to fix because the operating system is responsible for managing threads. So threads are expensive. We can create 1,000, 5,000, maybe 10,000. We can create 1,000,000. And this is a problem because we block them, so we need a lot of. So what can we do to get the throughput that we need? And we have a few options, yes? We can run more instances of our application, and this is the easiest possible solution. We just need money, we buy more servers, we run more instances, we have to create some load balancer. Of course, our application have to be prepared for scaling, but we just money, and this is the easiest solution, but we want to save money, so we want to find any other solution, yes? We can also take an approach that would keep us from blocking threads. And this is something, let's say, a natural solution, yes? Threads are expensive. We need a lot of threads because we block them, so maybe don't block. But the question is how? And of course, we can try to make threads cheaper. But as I mentioned, an operating system is responsible for managing threads. But so the question is how make threads cheaper, yes? And let's now focus on the second option. So we'll try to don't block threads. So instead of blocking the thread, we can return it to a pool with available threads when it waits for an input-output operations to complete. So the thread can serve other requests, yes? And this solution allows a high number of concurrent operations without consuming a high number of threads. And while it removes the limitation on throughput imposed by the scarcity of operating system threads, it comes at a high price. It requires something what is known as an asynchronous programming style, employing a separate set of input-output methods that don't wait for the input-output operations to complete, but rather, later on, signal their completion to a callback. And the most common way to provide a non-blocking approach in a Java ecosystem is by using reactive programming. Reactive programming is a paradigm based on the construction of asynchronous data processing pipelines. It combines an observer and iterator patterns and functional idioms to give you a sort of toolbox, enabling your application to create, combine, merge, filter, and transform data streams. Thanks to asynchronous processing, you are able to don't block threads, so to use the server resources efficiently. So it's a reaction to a problem that threads are expensive, yes, but of course, nothing for free. As you can see on the slide, we have a simple method here. This method is responsible for logging the user into the system. And as you can see, we have two input parameters, just login and password, and we want to return an access token. So the code is very simple. I think that maybe if someone is a programmer, even if someone is not a programmer, he can understand what we are doing here. So the first operation is finding the user in the database. Yes, so based on the provided login, we find the user in a database, or maybe we use some external system like MICROSERVICES to find the given user. We check if the user is activated. We verify the password. So if the one given by the user is equal to the one given set by the user during a registration process. We create some session and we send some notification, probably using some other microservice or maybe some queue. And we return an access token. But there are problems with this solution because we have the possible blocking operations here. So finding a user in a database or maybe finding a user in an external system is a potentially blocking operation because we have to invoke some HTTP operation or maybe some TCP operation, depends on the protocol which you use to communicate. And the the same is for saving sessions, so we can use some Redis or memcached. And this operation is also potentially blocking, like sending notification. And what we can do, as I mentioned, is to create a reactive approach. And this is the same method, create written based on a reactive approach. I used reactor core, but all reactive libraries are very similar, yes? So as you can see, the first difference is that we return mono of access token instead of plain access token, so we have some wrapper. And this code can seem a little bit more complicated, yes? Because we have find user by login, and then we have filters, which if empty, filters, which if empty, we have user map, flat map, we have some cache, zip with, flat map, then map. So this can be a little bit more complicated. And to be honest, it is, yes? So we have a reactive approach, we have a non-blocking approach, but we have to completely change our programming model to the one that allows us to decouple computation from threads, so we can have a lot of asynchronous operations, many more than the number of threads that we have. Many more than the number of threads that we have. But the cost of using it, is really high, yes? So the question is, it is worth to use reactive programming. And of course, it depends. It depends on the performance requirements. So if you, have a small system that is responsible for handling 2, 3, or maybe 5 requests per second, you don't need reactive programming. It depends also on the system architecture. If your system depends on some external services, if you have external service with a limited throughput, the reactive programming will not help you with changing the throughput for your external system. So your system can be very, very fast, but if your dependencies are not, your system will be not faster. It depends also on the use technologies, like libraries, like databases. If they support the non-blocking communication, like if your databases support the reactive approach, have libraries to communicate using this approach, and if your libraries are non-blocking or maybe blocking. And of course, it depends also on the people in the project, so if they are familiar with reactive and functional programming, to use this technology. And a very interesting question is, how big increase in performance can reactive approach bring? I dealt with this topic while writing my master thesis. I tested the performance for various architectures. Of course, I was not able to test all possible architectures, but I wanted to find factors that would allow me to estimate whether the use of reactive approach would make sense in a given case. And on this slide, you can see one of the systems prepared by me for the test purposes. And as you can see, we have 7 microservices here. We have 1 external system. We have 2 databases. And we have a lot of potentially blocking connections between microservices, yes? And I prepared this system based on 2 approaches, based on a classic, so blocking approach, and based on a non-blocking reactive approach. And I tested the performance difference. And on this slide, you can see the performance test result for 5 requests per second scenario. As you can see, we have 300 requests in total, and we have 0% of KO, with the average response times about 4 seconds. And now you can see the performance test result for the same system based on a reactive approach. So we also have 300 requests in total. We have 0% of KO, and the average response time is about 2 seconds. So the reactive approach is faster, but the classic approach is able to handle that load. And here you can see the performance test result for 10 requests per second. So as you can see, we have 600 requests in total, but we have 100% of KO. So this system was not able to handle this load. But using reactive approach, we have 0% of KO, and the average response time about 4 seconds. So reactive approach is faster, yes? Is able to handle more requests using the same server resources. So we save money because we have the same server resources, and we are able to handle more requests. And performance tests, these are for 15 requests per second. As you can see, using classic approach, we have, as expected, 100% of KO. And for reactive approach, we have some KOs, 9%, with the average response time about 21 seconds. So it has increased significantly, but in general, the system was able to handle that load. So as you can see, performance test results are pretty promising, yes? And that's why reactive approach is quite widely used today. For example, we can look at the number of users of Spring Web Flux platform, which makes the reactive programming as simple as possible. And now, I want to back to the slide again. So we discussed the first option, so running more instances of our application. So we just need money. We discussed the second option with changing the programming model to the one that would keep us from blocking threads. And we have also a last option, so make threads cheaper. And we'll try to do it now. So as I mentioned at the beginning of the presentation, JDK 19 was released just 2 days ago. And we have some interesting features here, but today we are most interested in virtual threads. Virtual threads, an introduction of virtual threads is an attempt by the JDK community to add a lightweight concurrency construct to Java. So one more time, it's a reaction to a problem that threads are expensive, but in a different way, yes? And of course, we have reactive programming, but the cost of using it is really high because we have to completely change our programming model. And now JDK says, hey, but the real bug is not a programming model. The real bug is that threads are expensive. So we can solve that problem and just write an ordinary straight sequential code using the features that the language already have. And it's gonna be great, yes, but operating systems cannot implement threads more efficiently because different languages and runtimes use a thread stack in a different ways. So the solution is to create threads on a different level, on the JVM level. And this is the purpose of this new JDK feature. So virtual threads are a lightweight implementation of threads that are provided by the Java virtual machine rather than operating system. Thanks to that, JVM can create virtual threads much faster and can store and manage them more efficiently. And now I will try to show you how it works in practice. I have to end presentation for a moment, and I hope for a second you will be able to see a code. Yes, you can see now. Okay, so we'll try to do some tests, and as you can see, we have very simple code here, just a main method. And I want to just start a given number of tasks using some executor, and the task will be very simple. I just will simulate the blocking call using just thread sleep invocation. So every task will be just sleeping for 1 second, and we'll try to check how many of this task we can run. So this is a simulation. Simulation of let's say blocking invocation. Yes. So as you can see, I have set the given number of tasks to 100 now, and I have a thread pool with 100 threads. And I will try to run the method. And as you can see, the method is completed successfully, and the duration execution time is equal to 1 second, about 1 second. And we now will try to run 1,000 of tasks. It's a very simple task, and as you can see, we have to wait for a moment for a completion, but it should complete. Yes, the duration is about 10 seconds. Yes, because we have 1,000 of tasks and we have only 100 of threads. So The solution is probably to change the number of threads to the 1000. And if I will run this one more time, you can see the execution time is about 1 second, just a little bit longer. And now I will try to maybe run 10,000 of tasks. So I will increase the number of threads. And as you can see, I have an error because I was not able to run on my computer. I was not able to create even 10,000 of threads. And this is a problem, yes, because we need it because we block them. And now we have the new JDK 19 feature. So I will change this executor to the new with virtual threads. And as you can see, there is no threads number, just new virtual threads per task. So new virtual threads will be created for every task because virtual threads are cheaper than standard operating system threads. And if I run this code, you can see that my code has completed successfully, and the execution time was about 2 seconds. So as you can see, now we have a lightweight concurrency construct in Java. But of course, the new threads are not faster. Yes, but someone can say it's super, yes, because we have a faster threads, but not. We have the only a cheaper thread, so we can create, for example, 100,000 threads. We can create maybe even million, but they are not faster. And now I will try to run some other examples. So maybe I will try to sort some array instead of just invoking thread slip. And as you can see, I just have a bubble sort. I have some test values to which I want to sort. And each task will be now responsible for sorting this array from the start. And I will try to run this code using the fixed number of operating system threads, so 8. And as you can see, the duration is about 50 milliseconds. And if I change it to the virtual threads, as you can see, the execution time has slightly increased, yes? Because we add some additional layer of abstraction that JVM have to handle. So virtual threads are not faster than operating system threads, but it allows us to make a blocking calls in a cheaper way. In my opinion, in the introduction of virtual threads is one of the most important features during last years, because we just can have a lot of blocking calls, and this will not longer be a problem. Yes, so our system, we can use it, and our system may be 2 times faster, thanks to just changing the executor. I will back to the presentation now. So we have to wait for a second. Okay, so what is the future of reactive programming if we already have a lightweight threads in Java? Some experts say that virtual threads are going to kill reactive programming because we no longer need it. I don't agree with this opinion, because reactive programming is not only about running code concurrently in a non-blocking way. It just provides us a more very powerful features. And if the only thing that you need is just spawning 1,000 of computations concurrently and returning the result, virtual threads will be sufficient for you. But reactive programming gives you more. It gives you support for backpressure, for task composability, for propagation of change. And as you can see, we have the backpressure here. So this is the idea that if you consume data from some source and you cannot keep up with consumption, you are slowing down the producer. So a consumer can say to the producer, hey, I'm able to handle only 2 or maybe 3 requests per second, just don't send me more. Or maybe can even say, hey, I'm able to handle more, so if you can, just send me more. And let's assume you need such feature and you don't use reactive programming and you have to implement back pressure, probably with a ton of bugs, yes? So having a nice implementation from reactive library is something very useful. Task composability is also a very powerful feature. It gives us the possibility to chain or zip multiple tasks together. It's something what completable futures give you to a certain degree, but you know that you can take two futures and compose them, but it is much more powerful, yes? And I will show you some example one more time in a code that was prepared by me for our internship, for our development internship. Okay, so we have some service and some external dependencies in this service, and the task for the interns was to implement some methods here. And as you can see, the first method is very simple. We just run some completable future from the user repository and use some then apply. The second method is also very simple. But the next one is a little bit more complicated because we have then compose, we have some completable futures inside the compose, and we have some then combine. So it's a little bit complicated, but let's say it's okay with the brevity of this method, yes. And we have some method get info about user, which is a very complicated. As you can see, we have some then compose, we have list of completable futures. So we create a stream of completable futures, and we use some map to list. We have some all off, we have some then apply, stream, map, completable future join, and some collect. So this is a little bit more complicated. And to handle errors, the interns have to write something like that, yes, because the API provided by the completable futures is not so rich. And now we have the same solution using the reactive framework. And as you can see, the first two methods are also very simple. But we have this last method, which you can see we have just get user and we have one flat map. So instead of writing this code, we can write this. So the task composability offered by the reactive stream library is much more powerful. So we have a very nice task composability, which I think we can use, for example, for asynchronous business processing. Maybe even running this code in a virtual threads pool if we just want to make a blocking call inside it, yes? And the question might be just why this code is can be shorter. Because we have a lot of operations in the Flux class, which is the class provided by the reactive framework. As you can see, we have a lot of methods. So it is really powerful. And we have to one more time wait for a second. Oh, we have some problem. Yes, we have some problem with threads. This is not a part of this presentation about threads, but as you can see, threads are expensive, yes? So I will try to run the presentation one more time. This is an unexpected behavior. This is not a part of the presentation. Okay, so task composability. Okay. The propagation of change is also a very interesting feature provided by reactive libraries. It's just a support for an event-driven model. So someone can say, we can use some external library to achieve it. And it's true, but having a nice implementation of event-driven model out of the box, why not? And it is worth to mention that reactive programming is still the fastest possible solution. Jetty experiments, Jetty is one of the most popular HTTP servers, and not only HTTP. Jetty experiments shown that it is more performant to use non-blocking input-output with standard operating system threads, because garbage collector is actually behaving better. And if you use virtual threads, you add some additional layer of abstraction that JVM and the garbage collector have to handle. And of course, the differences are not so big as they were in comparison to the reactive versus, so non-blocking versus blocking. But the reactive is still a little bit faster, but of course we have to wait for the final version of virtual threads, because now we have only a preview feature. So what is the future of the reactive programming? Yes, I think, so as you can see, reactive programming is something really powerful, yes? But we have to notice that the easiest thing for ordinary programmers is just writing and analyzing straight sequential code. That is much easier than transforming asynchronous processing pipelines, when we have to give up control hop statements, we have to give up simple loops, we have to give up clear stack traces, we have to give up profiling and debugging tools that we are used to use. And if your code doesn't work, just good luck, debug again. But it may also be the case that you will create system and you will start adding more and more features, to adding more and more abstractions to support, for example, BACKPRESSURE, or to add better task composability, or maybe some event-driven model, and you will reinvent reactive libraries yourself. So to sum up, I think that reactive programming will be back to its niche when it comes to applying it for entire systems. However, I still see cases when its use will make sense. Thank you very much.